Right, John Scott here. This is going to be looking at simple harmonic motion in a little bit more detail, and we're going to first of all derive some of the equations that we use for that. But first let's just talk very briefly about the general idea of simple harmonic motion. We can have some kind of spring attached to some kind of object, keeping it stable. As we pull the spring down, we provide it with some energy, so it's stored as elastic potential energy, and as we release it, it will oscillate up and down in this general way. This is one example. This would be called a spring motion one. As we describe this motion, when we let go of it, so say for instance we shorten it and then we let go of it, we'll see that its movement, its displacement, is described by what we would consider as a sine curve. Similarly, if we have a pendulum that is attached at the top, again at some kind of fixed location, maybe the ceiling, and we have the bob at the bottom, we will see that as we let go of this, it will describe a motion from left to right, being caused primarily by the force of gravity downwards, but of course as a vector, using our vector resolution across, it will actually end up with a net force towards the right there, and its gravitational potential energy at this side will be transferred to kinetic energy, moving across in this way, coming back up to this side here, and then it will return back as it has done with the spring. We will notice here that if we started it at the left hand side, it will also be described by a sine curve, and in this case from side to side. The sine curves are fairly straightforward to describe. They have an amplitude and a maximum height. The maximum value of a sine curve is 1, similar with cosine. And if we look at the maximum displacement, we would call that maximum displacement the amplitude A. And so the equation on the left hand side here, being described as a result of the angular displacement that is at, would be x being the displacement equals the maximum amplitude multiplied by sine of the angle at which it's actually located at a particular point in time. That actually applies to both this and this, although this was at the side. The maximum value of sine is 1, so the maximum value of x is therefore going to be, so x max is going to be equal to A, as we have described that as the amplitude. Now the next part of looking at this is actually just looking at, oops, let's take this back, is looking at the angle theta for a moment. Theta is actually a function of time, depending on the angular velocity omega multiplied by the time. So for example, if omega is equal to 2 pi radians per second, then if t is equal to 1 second, we'll find that omega is equal to 2 pi times 1, which equals 2 pi radians. So in terms of a circle, what we have here described is that it's actually moved times 0 is at the top, for instance, and we're moved all the way back again to that location there. If we set this to, as an example, 0.5 seconds, then instead of this arrow being back at this location here, it's actually pointing halfway. So it would be at 0.5 seconds, the angle would be pi radians. So we can express the displacement x to be equal to the amplitude multiplied by sine of the angular speed times t. This, of course, is an angle theta in radians. Okay, so let's go back to our equation here, and we're going to look at different aspects of this equation. So if we say that the displacement x is equal to the amplitude times sine of omega t, we could equally well say the same but for cosine. Depends on where we actually are on the using the maths and where we're starting our circle. For purposes of the maths that we're going to do here, I'm actually going to cross out sine there, and I'm going to use cos instead. It doesn't really matter, but cos starts at an angle of 0 at the value of 1. So if we were to draw that on a time-dependent graph, t going across, and this being the displacement, we'd actually start at the top, and we get a graph that looks something like this. So if we define the velocity to be equal to the change in displacement by a change in time, we will end up with an equation that looks like this. So the velocity is equal to of a cos of omega t divided by dt. If we now look at how we actually differentiate this, we have to use the chain rule. We have a constant inside here, which is omega. It's in respect to t. So what we end up with is first cos, the differential, first differential of cos is sine. We'll notice if we look at the gradient up here, it's a negative. So we have a. We still have omega t. And then using the chain rule, we end up with having to multiply. So clear this up a little bit. We have the velocity is equal to minus omega a sine omega t, which if we were to draw that, we would find that we start off at a negative value of minus omega A. So this value here is A. We're going to start at minus omega A. Remember, the value of sine takes on whatever it's been multiplied by at the beginning. So start at minus omega A. At the time when this is 0, here, sorry, correction. At the when the angle omega t is 0, which is here, we actually start at 0. But we're going to head in the negative direction. So when this value here is 0, we are going to be at a negative maximum. So in the next point we're going to have on this graph would be down here. And then it's going to return when this one is here. We're going to be back at this point. When it's here, we're going to be back at a maxima here. So on. So we're going to have the same graph, but it's going to be out of phase with the one above it. So this would describe this. Now the value, the maximum value for the velocity, let's call it Vmax, is going to be equal to this, but we'll give it a positive value because we're actually interested in a positive value. So Vmax, the maximum velocity, is going to be equal to omega times A. Lastly, we're going to look at the acceleration. So the acceleration, you will know, is the rate of change in velocity, which I think you would agree, because it's the second differential of this, is d squared x by dt squared. So what we need to do in order to get the acceleration is we need to use the velocity, which is described above as d of minus a omega sine of omega t by dt, and using the same rule as before. So we need to use the chain rule because we have constant, we have the t inside the brackets, which is what is a function of, and cos turns to sine, but it stays the same value. So we have minus a times omega times cos omega t, and then there we have to now multiply by omega again, so that becomes omega squared. So the acceleration at any given point in time is given by this equation, In the next video we will have a look at how that looks as a graph. So I'll save this for now, make your notes, and I'll catch up with you on the next video.